Hello everyone, thank you for joining today's webinar. I am Sumit Singh, an electric motor expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software from electrical and electronic design. Our products are mainly embedded in the most popular CAD platforms, namely SolidWorks and Autodesk Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. I request all the participants to please feel free to ask your questions using the chat box option, and we will address all the questions at the end of the presentation. Here is our today's agenda. First, we will go through the concept of Hallback array and its advantages and drawbacks for a Hallback array PM motors. Then we will look into its design challenges of Hallback array type PM motors. Then we will simulate 3 different models of PM motors, and we will use our EMWorks 2D simulation software to obtain the performance analysis. Later I'll demonstrate you the live model for one of the simulation, and then we'll have a Q&A session. Well, to begin with, the American scholar Mallinson discovered a peculiar permanent magnet structure and called it a magnetic curiosity in 1973 when he assembled a magnet structure. He was not aware of the applied value of this structure, but in 1979 Klaus Hallbach, an American scholar, discovered this special permanent magnet structure and gradually perfected it by making use of its magnetic fields. Finally, the so-called Hallback magnet was formed. A Hallback array is nothing but a type of specialized magnetic assembly. The Hallback magnetic ring is a combination of radial and parallel arrangement of the magnet. So let us look at the diagram. We have a radial arrangement of the magnet. So one is facing towards the north, and then the second magnet, the consecutive magnet, will be facing towards the south pole. Now the flux flowing between these arrangement is as shown here, which is in radial arrangement. Now there is another type of arrangement called tangential arrangement, where the magnets are the north pole and south pole are not facing each other. Here the flux path is leaving out from the north pole of the magnet and then entering back to its south pole. Now what if we combine both of these arrangement? So the third option is to combine the radial arrangement and the tangential arrangement of the permanent magnets. So here we can see. Now what if I merge both the arrangements? So instead of this blank spaces between the radial arrangement, if I just insert a tangential arrangement of the magnet, it will look something like this, which has been shown in figure C. So we will have a flux which is getting added upon on the top part of the magnet, which is the both, it's all in the same direction. But as you can see here, the direction of the magnetic flux for radial is opposite compared to the tangential arrangement, and hence the resultant would be something like this, which is shown in figure D. So as we can see, due to this arrangement of both radial and tangential, which is nothing but called as a Hallback arrangement of north pole and south pole of the magnets, we get a very strong magnetic field on one side of the magnet, and the magnetic field which cancels out and produce a nearly a zero magnetic flux on the below side. So well, this specialized arrangement is called the Hallback array. Hallback arrays now have many applications and are used in various range of systems or varying complexity. Now, if we can arrange this array in either linear form or circular form, it has its own applications. One of the simplest applications of linear Hallback arrays is in refrigerator magnets, as you might have seen in the door of the refrigerator magnets. In this case, the one-sided flux properties are used in order to boost the holding power of the magnets. Also, a more advanced example of linear Hallback array is in a maglev train track. The magnetic arrays lift the train a small distance above the track and can support a weight of up to 50 times that of the magnet. Maglev trains do not suffer from many of the frictional forces which slow down traditionally wheeled trains and are able to provide high speed transportation. For circular or ring form of Hallback array, permanent magnet motors are one of the best examples. Moving ahead with Hallback array arrangement, compared with the traditional motors, Hallback motors have many advantages. First is high power density. Now if we compare the traditional permanent magnet motor structure, the magnetic field intensity on the other side is greatly enhanced because of the superposition of the parallel magnetic field, and the radial magnetic field after the decomposition of the Hallback magnetic ring, which can effectively reduce the size of the motor and enhance the power density of the motor. Next advantage is no screwing required. In traditional permanent magnet motors, due to the unavoidable existence of harmonics in the air gap magnetic field, skewed slots are usually used in the stator rotor structure to weaken its influence. In Hallback motors, the stator and magnet rotor do not need skewed slots because of the high sinusoidal distribution of the air gap magnetic field and small harmonic content. Next we have rotor can be made up of non-core material. Because the self-shielding effect of the Hallback array magnets is no longer required to use of magnetic materials to provide access for the rotor, which not only provides a greater choice of materials for the rotor but also allows the system to have a lower moment of inertia and better rapid performance response. Next, Hallback array permanent magnet have high utilization rate. As a result of partial magnetization of the Hallback magnet, the permanent magnet has a higher working point, generally more than 0.9, which improves the utilization factor of the permanent magnet. Hallback arrays can be used with centralized windings, which is nothing but a concentrated winding. In traditional permanent magnet motors, distributed windings are often used to weaken the influence of the harmonic magnetomotive forces. Concentrated winding can be used in Hallback motor because of its high sinusoidal distribution of magnetic field and less influence of the harmonic magnetic field, and also it improves the coil fill factor since all the tooths are wound in a concentrated winding fashion. So using Hallback motor magnet arrangement, one can also reduce the torque ripple of the motor, thus greatly reducing the requirement of the motor bearings. So overall the torque pulsation is also get reduced. Now while talking about so many advantages of Hallback array PM motors, we have few disadvantages also. The main disadvantage of the Hallback array geometry or the arrangement is that it is difficult to assemble. All of the magnetic elements repel each other in Hallback array, which can create a variety of assembly issues. Also, the magnet which are going to be mounted on the rotor surface, or maybe we're going to insert inside the rotor cores, or need to be pre-magnetized. There is no facilities or options to magnetize these magnet after the assembly step is done. Therefore, since the magnetized permanent magnets are required, it creates the forces which need to be compacted so that it ensures the assembly will hold together during its operation. Another disadvantage is that the magnets are arranged in a direct or quasi-direct repelling conditions. This means the magnet is in the same array are acting to demagnetize their neighboring magnets. With a high coercivity alloy, this may not be an issue unless these temperatures are required in the application. So basically, as the operating temperature increases, a magnet becomes more susceptible to demagnetizing, and neighboring magnet demagnetization is occurred. Last, we have the cost of manufacturing. Since, as we discussed, as it is very difficult to assemble it, and we need very high strength glue and such that we need to combat these forces during the assembly process, its cost of manufacturing are basically higher compared to a radial flux PM motors. Moving ahead, so basically to design an electric machine is a challenging task, as its electromagnetic, thermal and mechanical performances are coupled and need to be taken into consideration at the same time. So the first challenge comes to design a Hallback array PM motor is to obtain its performance, such as its back EMF, air gap flux linkage, its electromagnetic torque and cogging torque, and also the torque pulsation, both at no load and at full load of operation. Second challenge is to optimize the magnet ratio. So it's very important to design a PM motor with a optimized magnet to pole ratio such that it leads to a better performance. Third is to estimate the magnitude of losses in different parts of the motor, whether it's stator or rotor core losses, winding losses or magnet losses. Also, in case of Hallback array PM motor, the estimation of forces, magnetic forces acting upon each other are very important, because here, due to its arrangement, all the magnetized PMs repel each other. So to make this design process simple and easier, EMWorks has various motor solution products for you. To begin with, first comes the Motor Wizard tool. It is a template-based motor design software that allows user to accurately solve both electric and magnetic problems. It includes electrostatic, magnetostatic and transient solvers, which is equipped with integrated analytical and finite element based solvers. Then comes the second product. We have EMWorks 2D. It is a 2D electromagnetic simulation software that uses the finite element to solve magnetic, electric and transient problems. EMWorks 2D allows you to study the effect of the geometry or simulation parameters changes on the design. It also allows to couple a transient magnetic study to mechanical motion and thermal. And then finally we have the third tool, which is EMS. It enables user to do both electric and magnetic simulations using the complete 3D geometry. EMS is a true multi-physics software that enables user to couple the magnetic and electric design to circuit, motion, thermal and structural analysis on the same model in a hassle-free integrated environment. So in our today's webinar, we will be using EMWorks 2D to simulate our Hallback array PM motor. So here are the specifications that we are going to use today for analysis. So basically we are going to simulate a 3-phase PM motor having a fixed stator for all the three models that we're going to simulate, having an outer diameter of 100 millimeter with a stack length of 100 millimeter, so that there will be a fair comparison since we're just going to play with the magnets. The number of poles are kept 10, having a slot number as 12. The base speed is kept very low and chosen to be 400 rpm. The number of coil turns are set to be 35, and we have used 1 millimeter air gap between the rotor and the stator core. And today we will be studying three different array arrangement where RMP is nothing but the ratio to magnet to pole pitch, and we will be choosing it as 1, 0.8 and 0.5. And since we are going to use EMWorks 2D software, we have simplified our 3D geometry into a 2D using a 2D simplification, and this is what we're going to simulate today. So to understand in a much better way, RMP, which is defined as a beta R by beta M. So as we can see in the diagram, the beta R by beta theta is the ratio between the first magnet, which is in the radial position, and the second magnet, which is in the tangential facing position. Total of this arc gives you nothing but beta M, that is a magnet arc. Now if you take the ratio of this radial facing PM over the total arc of the magnet, which gives you the ratio. So if we choose this RMP value as 1, which means the beta R over a beta M is 1, it's nothing but it's a conventional surface PM radial flux motor. Now to make it as a Hallback array arrangement, we have a choice to choose either of this value but not equal to 1. So we chose two different combination. One is 0.8 where the beta theta magnet value is lesser compared to the beta R, and therefore its ratio is 0.8. And then we have the third model where both are equal, and which leads to 0.5 RMP ratio. So to begin the performance analysis in EMWorks 2D software, first different study settings are needed to be done, such as material, boundary conditions, mesh and windings. So using a material section, EMWorks 2D provides the user a wide variety of materials. So from among this you can set the materials for your magnet, for the rotor and the stator cores, and the type of winding. Then we set a boundary condition as a magnetic vector potential to an outer air of the model, and then we compute the torque by selecting all the rotor faces, and then we set the mesh parameters, and then finally we choose whether it's a voltage control or current control excitation, and we can also set its frequency, amplitude and its phase delay. So once we set all these parameters into a software, we are ready to simulate our model. So first we'll look into the results of the conventional surface PA motor, where the permanent magnet to pole ratio is 1. So for conventional surface mounted PM motor, under no load analysis, we obtain a cogging torque of around 0.22 Newton meter. So this is usually performed at very low revolution per second, and we can see here that the cogging torque magnitude is very close to 0.22 Newton meter. Also we obtained its magnetic flux animation at base speed, and as we can see, the flux passes through one pole to the next pole in a radial fashion. And at the bottom you can also see the permanent magnet vector flux plot. For conventional surface motor PM, we have obtained its back EMF, which is not very good, as close to sinusoidal and contains lot of harmonics, and it's all due to its magnet arrangement. Since it has a radial flux surface mounted PM motor, so it get a very flat top at the back EMF, and we can also see its flux linkage, which is sinusoidal in nature due to its winding arrangement. Next, we obtained its on-load torque, and the magnitude is close to 6.5 Newton meter, and at the on-load analysis we obtained its magnetic flux density. So as we can see, the flux saturating at the tooth or near the stator back iron is close to 1.8 Tesla, which is well within the limit of the material, and the flux density plot looks fine, and as the rotor rotates, we have a rotating magnetic field. Now moving on to the Hallback array arrangement with the magnet ratio as 0.8. So here, as you can see in the picture, we have a red and the blue magnets, which represents the radial arrangement, and the yellow and the green are the tangential arrangement of the magnet, and the ratio between the radial and the tangential magnets is close to 0.8. So we can see here, as it eliminates the air gap magnetic flux harmonics, the overall Cogging torque has also reduced to 0.13 Newton meter, and which is lesser compared to the conventional surface mounted PM motor. And we can also see its magnetic flux animation here, and also the magnetic flux density saturating at the tooth body or the stator back iron is close to 1.5 Tesla. And we can see here, due to this Hallback arrangement, we have a flux passing between the poles, but although the ratio of the radial magnet arrangement was very high, so still we have a flux mainly flowing due to a radial magnet. Similarly, we can see its magnetic vector plot using the EMWorks 2D software and understand the magnetic flux path. Next, we obtained its back EMF and flux linkage. There is not a much difference between the surface mounted PMSM and the Hallback array if we use a ratio of 0.8. Still, the majority portion of the pole arc is dominated by a radial flux magnet, and we get a flat top at the back EMF waveform. And also, this is not even like closer to sinusoidal waveform and contains lot of harmonics. For Hallback array arrangement PM motor with 0.8, we get a good flux linkage, and it's due to its concentrated winding arrangement. We obtained its on-load analysis, and it was interesting to see here that the overall torque density of the motor has increased, and in the previous conventional surface mounted PMSM we got around 6.3 Newton meter, but now we get around 10.1 or 10.2 Newton meter torque. So therefore, due to the usage of Hallback array arrangement, the overall torque density of the motor has improved. And you can see the tooth of these stator cores are highly saturated, up to 1.9 to 2 Tesla. It gets stronger by using this Hallback array arrangement. Next, we have a magnet ratio with 0.5, where, as you can see, all the magnets, whether the red and the blue as radial arrangement and the yellow and the green as tangential arrangement, are share the equal magnitude of magnet arc. And let's see its result. So it was observed that the no load Cogging torque has further reduced. Therefore, this model comes out as the best to reduce the torque ripple of your machine among the three model. And we can also see that since all the flux paths are within the magnet portion, it starts from one radial, moves to the next tangential magnet, and then it's leave to the stator core and then again returns back to the magnet. There is a very less amount of magnetic flux flowing through the rotor cores. Also at the same time we can see its coercivity direction as shown at the bottom of the magnet vector plot. So finally we obtained its back EMF and flux linkage, and now we see here that the back EMF is not perfectly, but it's very close to sinusoidal, and it may also contain some little harmonics, but overall the THD of this third model, where we have used a magnet ratio to pole arc as 0.5, leads to a sinusoidal back EMF, and also the flux linkage is almost the same as the other two models. Now if we obtained its on-load analysis, the electromagnetic torque is almost similar to what we obtained from the surface PMSM machine, but as we can see, the flux density in the motor has further increased, but as you can see, the majority portion of the stator tooth and the body is still well within the limit, near close to 2 Tesla. So moving ahead, let us compare all the three different models. So from on-load analysis, we observed that the Hallback arrangement of permanent magnet helps to reduce the torque pulsation, which was one of the greatest advantages of using this array arrangement. So as the red represents for a conventional surface mounted permanent magnet where the ratio is equivalent to unity, and as we can see, due to the usage of Hallback arrangement, we get two different torque magnitude. One is higher compared to the surface mounted, and second one is lower. So that's all depends on what amount of ratio you have been using. So it's very important to optimize the ratio of your Hallback array arrangement such that it leads to a higher torque density of the motor. Also, even though the torque was better for magnet ratio of 0.8, but we can see the back EMF is much better or closer to sinusoidal in case of magnet ratio with 0.5. So now it becomes a trade-off between a better back EMF or whether a high torque density is a requirement. So it depends on what is the performance criteria and whether you need to reduce the torque ripple or whether you want to have a lower better power factor of your motor. So it depends, and accordingly you have to size your magnet arc. Next, which analysis is the force calculation. So the force density plots for Hallback array and conventional surface PMSM was obtained, and as we can see, the force density in case of Hallback arrangement is close to 1.78 into 10 to the power 10 Newton per meter cube, whereas for the force density for the surface mounted PM is lesser and close to 3.01 into 10 to the power 9 Newton per meter cube. So as we can see, the force density is almost increased 6 times in case of Hallback array arrangement. So this amount of force density need to be taken care of while prototyping such type of array magnets. So to summarize all the three models, and if we just obtain its torque magnitude, the highest torque, which is close to 10.1 Newton meter, was for the second model, which has a Hallback array ratio of 0.8, and the base speed was kept the same to have a fair compression, and also the stator and the windings were same for all the three models, and we obtained the power highest for 0.8. And also, since the volume of the overall machine is same and the torque is higher for the second model, we get the higher torque density also for the second model, and then comes for the first, which is surface mounted, and then comes for the third model, which has a ratio of 0.5. but also we obtained that the back EMF and the flux linkage was much better for model having a ratio of 0.5. so overall, for us, the one of the important criteria was to obtain the torque density, therefore 0.8 gets a better result. So let's move into the live demonstration of our model. So here we are into our SolidWorks platform. We can always use our setting option to add the EMWorks 2D software into our SolidWorks, and you can go to Tools, click on the EMWorks products, and you can launch either the EMS or EMWorks 2D. So for our today's analysis, we have used EMWorks 2D. So once we are here, this is how it looks like. We need to create a study. We have created a transient magnetic study with, you can set the start time, end time, and you can set the rotation speed, and then comes the material setting. So for our today Hallback array PM rotor, we have set the magnet as N48 grade, and we have taken the rotor core and the stator core as M19 with 0.5 millimeter thickness lamination, and then we have a copper winding, and we have set the outer air region and the band, rotational band, as air. Once we are done with the material setting, we go to load restraint, where we need to set the magnetic vector potential as air around the motor simulation platform, and then we select the forces that we need to calculate. And for our today's analysis, we have used a torque computation for the rotor core. Then we set the mesh, and we can see how the mesh looks like. So here is a mesh arrangement for our today's analysis. Once we are done with the mesh setting, we have to create a winding configuration. So here we have winding 1, which represent for phase A, phase B, and phase C. And under phase A, which is termed as winding 1, we have a different set of coils, which is a go path, and then we have different set of coils which act as a return path for the concentrated winding arrangement. Similarly, also we can see its current direction. So here, as we can see, we are having a current direction coming out of the screen, and similarly if we go for another set of coils, we can see how the current directions are assigned to this coil. So let's hide this current direction, and we can click to view its front view. So once we are done with the winding setting, you need to go click on the right side of the study, and then we run the model. So once we are done with the computation, based on the accuracy chosen, the time will be taken, and you'll get 2D results as shown here in the result tab. So here we get since we have run the on-load analysis, I'll be interested to see the torque magnitude. So I click on the torque, then I select this parameter and add into my parameter, and then plot preview. You can get its torque. You can always use your pop-up plot option to get its data in a table format. Here you get a time versus torque table. Also, you can export this data into an Excel file. Similarly, I will be interested to see its flux linkage. So we have all the 3-phase flux linkage. We select all of them, add to our parameters, and then plot preview. And since we have run for a lot of cycles, you can see such type of plot. And you can click on the pop-up plot and get it stable, and also you can change its legend or general setting, or you can even change these access properties and anything which will look good for our presentation. So once we click on the right click, you can choose the type of plot format you're interested in, whether fringe, vector, contour lines, and also if you need overlay with mesh or contour or vector, you can choose any one of them. So let's see the magnetic flux density plot. So here we get the magnetic flux density plot. You can also look at its animation by clicking on the right click of the magnetic flux density plot and click animate versus time. Also we can see its current density, so it's very important factor since we have designed our motor for air cooled. We need to know its current density magnitude, and for any totally enclosed fan cooled type of motor, the current density is good around 5 to 6 ampere per meter square. So that's what we get. So we have got a 5.9 into 10 to the power 6 ampere per meter square as the current density of our designed motor, so which is a good design for a air cooled type of motor. If you use a liquid cooled or water cooled, you can go for a higher current density. So these are the results, and there are many more which you can go through it and get obtained its electromagnetic performances of this motor. So well, coming back to our presentation, now I would like to conclude our today's webinar. So in today's webinar, Hallback array permanent magnet motor topology was simulated using an EMWorks 2D software. We saw its Cogn torque, back EMF, flux linkage, and on load analysis side we saw its electromagnetic torque and also its magnetic flux density plots. So various results were demonstrated for our participants, and we can conclude from our analysis that the Hallback motor with a magnet ratio of 0.8 achieved 35% higher torque density compared to the conventional surface PA motor, but at the same time the force density was almost 5.9 times higher than the conventional surface permanent magnet motor. So this way you can simulate your Hallback array arrangement and you can obtain its performance. You can optimize the magnet ratio and get the result which is as per the requirement or the constraint of your design. So here are the references, and thank you once again everyone for attending today's webinar. Now the session is open for a question and answer. Thank you.